All right, today we're going to go over software-defined radios. As you can imagine, a software-defined radio is a radio that is defined by software. All right, jokes aside, traditional radios are hardware fixed, so they're dedicated to a particular use or RF band. So one radio that's exceptional at one job. The software-defined radio gives significantly more flexibility, um, and and you're able to tune any frequency within the device's range. Now, what you gain in that flexibility is a little bit of complication um, on antenna selection. Like, you have to have the right antenna for the job still, um, but the benefit is that you can tune to any frequency in the range that device is capable of tuning to, and then because you're already hooked up to your computer natively, you have the opportunity to run like all the decode pipelines you want and build, these full decode pipelines where you're already working. So pretty slick. And then of course you can record straight to a file for future analysis, or offline analysis. And you don't have to swap out hardware again, with the exception of the antenna. But for our purposes, we're going to be focusing on the RTL SDR, which is a USB to device. It works on all the OSs. So I've got some install instructions here to get started, at least get the driver set up for you. And it has a wide enough range for our intended purpose. Do be careful if you have a V4 versus a V3. The driver is different, so you just need to be mindful of that. We're all going to be focused on V3 here, and I've got a table here with some common frequency ranges. So 433 megahertz is your unlicensed ISM band. So there's a ton of signals in there. Everything around your house is running 433. Um, Garage doors could be on there, remotes, all your sensors, rain sensors, a ton of stuff. It's unlicensed, right? So it's super cheap and easy to use. You don't need to be licensed. There's the benefit, and maybe the trouble. It is noisy, so depending on where you're at, you could be totally overwhelmed with with trying to figure out which signal is the one you're looking for. Um, 315 megahertz is also fairly common in North America. Uh, a lot of garage doors and definitely tire pressure sensors. The tire pressure sensors on most modern cars have either evolved to Bluetooth, or or they're triggered by a centrifugal switch. So the vehicles have to be moving. So and they don't transmit often. It's not like a high speed bus or something that needs to be updated real time. So you know a vehicle has to be traveling over 20 miles an hour and only transmits every 1 minute or so. They're a little bit tough to catch if you are stationary. Those are more likely to be caught when you're driving with traffic, if that makes sense. Not to say it can't happen. As a matter of fact, I'll show you it happening here in a sec. And then just the last one I'll highlight is the 1090 megahertz, which is just a fun wow factor for getting into SDRs. It's the beacons from all the airplanes overhead. So I'll show you that here in a sec. Some different modulation types. I don't want to make this a class on RF theory or anything, but it is important for you to recognize the different types of modulation so that you know what decoder tools you want to start looking at. It at least gets you pointed in the right direction, if you can immediately identify. And so here's some examples. Again, I'm not going to try to make it into an RF theory class, but they all look significantly different, right? And we'll talk about some of them here in a sec. I'll zoom in on, for example, the on-off keying. So we do have one of our challenges that uses this, and really the thing that you need to be able to do is measure the short bits and the long bits. So the short bits are short in duration, long bits are long in duration. You're trying to measure the microseconds that each one is on. And so how that translates is usually the short pulse is a 0 and long pulse is a 1, and then the intergap space is fixed. So instead of 1, drop to 0, 1, drop to 0, and that, which would be what you would imagine, like we'll talk about it later. But the important part is that intersymbol gap is fixed. So to represent a 1, we're doing a long pulse, and to represent a 0, we're doing a short pulse. Okay, more to follow. Neat. And you could actually zoom in and you could actually measure all that, or you could just let the computers do the work. I'm a fan of that. So that's what we'll show you here in a sec. This is probably one of the first commands you'll run if you're running in the 433 megahertz band. And the -A is for analysis mode, so it will analyze the signals. I was going to wait, but let me just show you what that looks like here. Right there. So this is a signal that I'm generating here. Here's the command, so RTL 433-A, like we mentioned, and then I tuned it to a particular frequency that I'm transmitting on. And I happen to know that the short pulse is 500 and the long pulse is 1500 for this one. And so it even gives me like the command that I can run that will likely decode this signal. So that's pretty slick. Again, I just ran this analysis command, and the pulse width identified correctly, close enough that 500 and 1500 are my short and long bits. Pretty cool. That's going to mean something here in the near future. All right, so that's on-off keying with pulse width modulation, which is a mouthful. All right, so I'm not going to go over all the modulation types, just the ones that are relevant in the immediate future. So frequency shift keying is not specific to, but POC/SAG uses FSK. POC/SAG is pagers, just like you imagine, pagers from the 90s. Everybody had one. Everybody cool had one. I don't know if that's true. We're not have to go into the signal, but the important part is that 1200 baud is the common one, and I can show you what that looks like a couple different ways. I'm kind of like getting ahead on my demos, but it's fun. So POC/SAG looks like this, which is just gibberish until you run it through a decoder. I've built a software, if I can find it here. Where'd it go? There we are. I've built a software that can analyze this and decode it for you, so you can see the messages. This is a real. I mean, this is really running. So here, this is kind of neat. This just popped up. I wasn't expecting, but APRS is digital location publishing from ham operators. So that's kind of neat, like sending out their location and stuff. All right, that was a aside. This is actually POC/SAG messages in use, so it's used frequently for emergency management. It's a good clean signal that you can transmit far and wide. I'm sitting here with a relatively small antenna, and I'm probably 40 miles from where this is coming from, which is pretty slick. This is my area's emergency tactical system. So we've got like an emergency at this address, this location. We've got fire being called out. Details. Something happened. We don't need to get into the details, but this decodes and shows me the emergency messages coming through. So that's pretty neat. And I mentioned airplane tracking. So let me just turn that on. I'll get that going. We'll come back to it here. I got a couple different ways of showing you that one. But since we're already in the software, all right, so I wanted to show you what the signal looks like so that you can recognize POCSEG or pager messages if you see it, or at least potentially pager messages. I am not going to go into the entire structure, but it's not too terrible. And like we saw here, it's not a straightforward decoding. So those messages that you looked at in the software are these messages. It's the same messages. So something is wrong in how these are being decoded, and I'll let you figure out what that is. But this is close to the command that that we actually want to use to decode these into something readable. All right. Your toolkit is going to look different than my toolkit. I am building my own. I can't bring over now. I am building my own, as you saw, and that's a way of doing it. I think the easiest way to go is the command line first. I don't recommend building your own software if you don't have to, but have a particular use case. And lots of other people have already built it, right? So SDR++, let me show you what that looks like. That's pretty good, and it's got plugins you can integrate with, and you get a nice clean waterfall. It just works. It works really easy and quick. Download it, install it, press play, and you're good to go. Like, you're already seeing signal pop up. This is cheating. This is FM broadcast, right? Kind of neat. You can listen to the radio, I guess. All right, so that was software plus SDR++. Just one GUI-based tool. Another simple GUI is GQRX. That is default installed in Kali, so that comes in handy. Command line tools for all kinds of stuff. And again, if you're in the 433 megahertz band, that ISM band that we talked about, you would specifically use RTL 433 as opposed to RTL SDR, because it automatically decodes stuff for you, which is super handy. URH is getting a little more crazy, but super powerful tool for running full decode pipelines and especially on custom signals. CyberChef, you're all intimately familiar with, I imagine. All right, so I just showed you the waterfall, so we can kind of skip this slide, but it's the waterfall, so it's falling down. So the newest signal is at the top, and then here's just a couple different signals. This like slanted line here is what that chirp looks like from the LoRa radios from last year. And then we've got some on-off keying. We've got some like a carrier tone. And then like left to right is your frequency spectrum. This is all kind of straightforward and obvious as soon as you start it up. All right, one thing to be mindful of is your gain. So let me see if I can demonstrate this real quick. My waterfall is going here, but my gain is keeping it under control, which I like. But if I crank the gain up, you can see I'm getting some noise here. I get a lot of noise, and that's really the point and the problem. On the flip side, if I turn my gain all the way down, if I turn it down, my signal kind of starts to disappear, right? So it'd be akin to like dropping it down here. It disappears, and then it has to be a really strong high peak signal for it to show up at all, as opposed to like turning my gain up a little bit, getting the noise floor set so that I can see signal, and then I've got a threshold here, like a automatic detection for the noise threshold that it has to break before signals will decode. All that's just fun. I'm not seeing airplanes right now. We'll come back to that. Okay. Back to the slide here, though. The gain settings are critical because you're gonna like if you amplify noise, you're just gonna get more noise. If you amplify, if you don't amplify enough, like if you have too low of gain, your signal gets lost in the noise. You can't decode anything. It doesn't break the threshold, right? So you need to find that optimal gain, and that's part of the art. You're gonna have to play with it. So if you see the signal, or if you don't see the signal that you know should be there, then I would start here. Make sure that you're looking in the right frequency, and then play with the gain. All right, here's a couple of commands. Like I mentioned, the 433 band's super simple because with just know your switches, know the options for the command, and um, and you'll be able to do a whole heck of a lot with it. I'll show you some more examples here in a sec. Right now, let's look at the POXAG. I already showed you, but again, here's the structure of it. So we would have to. You would have to take the message and then run it through this, right? So figure out what the sync word is, what the address is, what the message is, etc. Okay. And here's a gotcha, fun to know. And again, POXAG 1200 is the common one. That's what we're going to use. So you're welcome for that clue. But there are other pager baud rates out there. I already showed you what the messages look like, so let's keep going. Yep, we did that. All right. URH again. Here's some notes on it, but easy to install, super powerful, like really powerful, and complicated beyond the scope of this video. But I wanted to at least mention it. All right, and then so it's important too that when you see things like this, this is not a gotcha. This is not a perfect example, but like it doesn't necessarily mean that you're wrong, that you have the wrong thing or it's not decoding right. It is possible, it is probable that there is some sort of other encoding applied. Some of it's obvious. We can like easily identify hex and base 64. Some of it's a little less obvious, but you would expect to know these things either because you're looking for a particular signal with characteristics that are known to you, or you have some other clues leading you in that direction, right? Just, I guess what I'm saying here is if your decode looks like garbage, make sure that it's garbage and not just something that needs to be further decoded. Like you could decode, you could perfectly decode the signal into something, into letters and numbers and equal signs, let's say, and it's still not reading like ASCII words. You might still have to decode. Okay, I think I've said it enough times. Oh, before we move on, one more thing. It also might not be in the message itself, right? So what you're looking for, if I were a nefarious actor and I had, let's say, I had a tire pressure sensor that doesn't normally show up in North America, and I wanted to exfil data, I could exfil exactly that much data as long as I want. I could put it there. I could put it in the pressure reading. I could put it in battery or temperature. I could put it in any of these fields, but the maximum, like the biggest place for me to put that data is right here. Now this is decoded, so you're not seeing the raw, the raw bytes, but this is the biggest contiguous string of bytes that I can put together for one little bit of data, right? So granted, this would take a long time to exfil anything meaningful, but as an option, as an idea for exfilling data, for whatever reason you have to like secretly exfil data. Um, you could use a tire pressure sensor, and somebody's next to you and they're collecting it, and you're not interacting otherwise, and whatever, it's a parked car or something. You could be uh, into that kind of stuff. I don't know. Okay, let's see. I'll show you some more stuff here in a sec. Um, all right, so the capture workflow, right? So you're gonna start with something, either curiosity or clues or whatever, right? Leads you to go looking at signals, because that's not what most people do on Saturdays. Uh, you're gonna go locate the signal that you want. So you're gonna scan around and try to find. Let me pull this over while I'm talking. See if we can tune to 4.3.0, and we'll see if anything pops up here in a sec. I'll put that aside for now. I just want to show you that I did it. All right, so we're going to locate some signals, and then we're going to try to decode them, or we're going to first characterize them. Like, what modulation are we seeing? What kind of timing do we see? What shape is it, etc. And that's going to lead us to the type of decoders that we need. So how can we capture this uh, and save it off to a source file that we can analyze then later? The reason you want to save it off to a source file is because that signal might not happen all the time. So it's like, if again, those tire pressure sensors, if you have one that fires every 1 minute and that car was moving past you, like if you didn't record it, it's gone, right? And you'd never be able to go back or you'd have to catch up to the car, I guess. But you wouldn't be able to, have that signal come back. It's a one and done, kind of thing. So do collect it. Aim for several iterations of it, right? So maybe a better example would be the pager messages, right? You can tell that it's pager messages. You've identified it. It's where you expect it to be. It looks right. Capture many of them, so that you have, because maybe the noise is a little bit different. Maybe you had some interference. Maybe you started the collection halfway through a packet, through a burst. So capture several is, I guess, the point, and with the idea that maybe the first one and the last one at least are going to be cut off, or something wrong with them, right? And then you're going to go through and try to decode stuff. And then if the easy decoding doesn't work, then you're going to have to get into more powerful tools and build your own pipelines and extract things, like that. And then ultimately, I put CyberChef in here, but whatever, you could base 64 decode, whatever the encoding is. Just remember that it is possible that it is still encoded and properly, like the signal was decoded and you still have encoding to worry about. Okay, I think I've said it 12 times now. It should be fairly obvious. Some common mistakes. I think the gain is probably, well, obviously the center frequency. So, like if I'm trying to listen to the radio, let's say, and I have a signal here, if my center tuning is, well, if I'm narrowband instead of wideband, anyway, if my center tuning is off a little bit, I won't be able to decode the audio. So most tools, you can just click in the spectrum analyzer or your waterfall at like roughly the center here of the signal, and it will retune. And you can see the whole waterfall shift, right? So you've retuned, and you can see that it did tune a little bit different than perfect, but that's fine. And that might be that small shift, given especially a narrow bandwidth type signal, is going to be the difference between being able to decode something or not. So that's why I put the wrong center frequency as the first common mistake, because you might be close and off just enough that you're not getting what you need to. Um, Sample rate, fine. The gain we already talked about, but really you got to play with that. So if you're on the signal and you see the signal, uh, or I guess more importantly, if you don't see the signal, play with the gain and make sure you're able to you know make it look right in the spectrum analyzer and the waterfall, so that so that you don't have too much noise, but you have enough signal at the same time. All right, and then again, okay, I've really stomped my foot on this one. So don't assume ASCII. Okay, so we're gonna do this right now. So I actually already showed you this analyzer here. Um, that analysis mode for the 433 band is crucial because you're more than welcome to go measure the millisecond bursts, but again, it's better to have the computer do it for you. It's certainly more accurate, and with it giving you a flex decoder string here, all the work's done for you. It guesses the modulation type, it guesses the short and long pulses, and the reset and the thresholds. So anyway, super powerful, like really easy to use, and is going to give you the answer most of the time. All right, and some other notes here, FYI. This is specific to the upcoming challenge. You will want to have the drivers for RTL SDR installed, V3. Make sure that you have those installed. Again, GQRX is already installed on Kali typically, and you're welcome to. I would also install some of the command line stuff. It's a good place to start. Using URH or Universal Radio Hacker or SDR Sharp or SDR++ or whatever other tool, your own custom one that you wrote, is great. Just make sure that you have considered some of the protocols that you might be looking for, and make sure that you have like a decode pipeline already built. You don't want to try to find the plugin, figure out how to use it, configure it, all that. You want to have done it before you're on the clock, let's say. All right. Record first. I think that's always healthy. And then the payload may not be in plain ASCII. One decoder won't catch everything, so you're gonna have to play around a little bit. All of the signals that I'm generating look realistic, so it shouldn't be. It's not meant to trick anybody. And then here's a quick reference guide. For whoever needs it, let's say. Give me one sec. I'm going to pull up my software and I'll show you some fun stuff. Just one sec. All right, so I went ahead and brought up some flight tracking. I got it started here just to make sure that there was a flight overhead. I had to take a pause here, but this is the command. So again, many different ways you could do this, but by running this simple command on just my laptop with the RTL SDR plugged in, I can already see flights being tracked. So I got their lat long, their speed, their heading, their altitude. Kind of neat. Doesn't mean a lot to me in text, but we can make the computers do some work here. And so we could track, flights, which is kind of neat, and add some information here. So we can add, let's see, so a Delta Airlines flight. What are they squawking? Nothing in this case, or at least we're not decoding it. That was that one. And what do we have? Alaska. What's this one? Yeah, probably Alaska Airlines. Sometimes you get more than others, but kind of neat. Track them across, where you're at or whatever. The same is true for ships. The APRS message that we saw earlier, if that had location in it, we would have seen that pop up on the map too. So again, like The text decoding, cool, but a little bit of wow factor here. You could do, we've got weather balloons. You could do, yeah, again, the aircraft, the boats. You could do weather faxes. You track the International Space Station. All kinds of fun stuff with these radios. Let me tune to. I've got my signal generator here, so let me get something kicked off. We're going to go to build a pipeline. I want to do tire pressures on 315. And we should see, again, it's relatively slow, but we should see the signal like very obviously show up here as we're tuned to the right area. I'm going to up the gain here a little bit because I'm not seeing it yet. And yeah, because we're not in the right spot. 315. 315-ish. Where's it at? There we go. Okay, let's see if there's our TPOS. Stop. Pause. All right, so here's our tire pressure monitor coming in here. Again, I showed you the Citron one on the command line. That is here, right? And this is just a visual representation of it. So I built this neat little thing, shows all the tires that pop up. So there's stuff you can do with it is the point. Like neat that you get it decoded on the command line. It's pretty cool. The RTL 433 does a lot of the work for you, but then you can visualize it however you want after that once you've figured out how to decode the signal. And really like decoding the signal is the challenge here. Let me just click through my tabs and make sure I showed you everything. Yep, pulse width analysis. We got the tire pressure monitors because that's fun. The POCSAG pager messaging. Again, that's you have to understand the structure of it. You can feed that into multipon. You just have to figure out what the right command is for the signal that you're going after. You saw the example of mine here for the emergency management stuff, and then flight tracking. These are just a couple of examples of like the fun stuff you can do with this. Again, a million different tools and all the signals in the world to play with, and that's it. So I think this challenge will be fun. You're going to get a couple of different signals, and they will not be straight ASCII. So if you made it this far and haven't heard that yet, then there you are.